Hey there, y'all. Today we're going to look at 2.5 on interpreting solutions of inequalities. In this section, we'll be able to interpret the solutions of inequalities and be able to solve one-step inequalities. For this standard, we are solving linear equations and inequalities in one variable, including equations with coefficients represented by letters. So let's review a couple things that we should know from middle school, but again, let's just talk about what we need to know to be able to work with inequalities. We have 5 symbols for inequalities, and these 5 symbols are going to define how relationships work. And so this first symbol, and when we think about the symbols, we need to think about, you might remember your middle school, elementary teacher talking about the gator wanting to eat more. Well, if we put X and Y here, and we read left to right, X is greater than Y, so that's what we want to say. So this is the greater than symbol. And when we face it the other way, X is now not the larger because it's open towards the Y, and so X is less than Y, because we always read from left to right in English, and we read from left to right in math. And so we have those two symbols. But then we could throw this little bar underneath those two symbols, and that little bar underneath means equal to. And so when we combine it with the greater than symbol, it is greater than or equal to. Now, it's not greater than and equal to, so it can't be both. It has to be one or the other. And so that's why we can statements like 5 is greater than or equal to 4 and 5 is greater than or equal to 5 are both true statements, because this is true because 5 is larger than the 4. This is true because 5 is equal to the 5. Okay? And then when we flip that sign around, it's the less than symbol with that equal to part below it. So less than or equal to. The final symbol's a little different. So if I've got my X and my Y, this is an equal sign with a slash through it. And so when we have the slash through it, that means that we're not doing that. So this means that it is not equal to. And what that symbol means is that 4 is not equal to 3, right? And so we're just stating a factual thing that something is not equal to a different number. But when we have like X is not equal to 3, we're saying that X can be any number except what's listed on the other side. So in this case, 3. Okay. So we're going to look at some examples of how to solve one-step inequalities. We've got some examples here of how to graph these first. And so we have X is greater than 5. Now, when you're graphing these on a number line, what you need to do is not draw a number line with 20, 30, 50 numbers on it. All I need is 3 numbers. We call this number on the right side the critical value. Now, this critical value is going to tell us what's important. And so in this problem, what's important is the 5. Now, what's to the left of 5? Well, to the left of 5 is 4, and to the right of 5 is 6. And so what we're going to do is we're either going to put a circle or a dot on the critical value. And so in this case, because we're not equal to, there's no equal to bar, we're going to put a circle. So again, we're going to put a circle if it's just greater than or less than. We're going to put a dot if that symbol is greater than or equal to or less than or equal to. So the key piece is that with the equal to part, I'm going to put a dot. With no equal to part, I'm going to put a circle. But that just tells me what's happening at the critical value. This statement says that X is greater than 5, so there's numbers that are larger than 5 that work for this. And so we need to ask ourselves, is 6 greater than 5 or is 4 greater than 5? Well, of course, 6 is greater than 5. So my shading will go from the 5 towards the 6 and continue on. And so our graph would look like this. We'll continue that through the other examples. So let's look at example 1b. Similar problem, now we have X is greater than or equal to 5. And so again, we're going to draw our number line. And in the middle, we're going to put 5. To the left of 5 is 4. To the right of 5 is 6. And so in this case, we're looking, okay, we are equal to, so at 5, I'm going to put a dot. And then let's judge. Is 4 greater than 5 or is 6 greater than 5? Well, again, 6 is greater than 5. So we shade towards the 6. Now, some of you might have been taught to use the arrow, and it always goes the direction of the arrow. But I'm here to tell you that that's not always true. Because if I rewrite this problem as 5 is less than or equal to x, then what we have going on is we're still a dot at 5 because we're equal to. But if we're judging this statement and we're asking ourselves which one is going to work, is 5 less than 4 or is 5 less than 6? Well, 5 is less than 6, so we would still shade towards the 6. And so that's why when you're testing these values to understand which way it's shading, what you need to do is test the values, one on each side. All right, so I want you to try examples 1C and 1D here. You have 7 is less than m and 7 is less than or equal to, or sorry, m is less than or equal to 7. I want you to graph both of those, use the correct shadings and the correct type of circle or dot. So pause the video here, try those two problems, and then come back. So in example 1C, what we see is we need to draw our number line. And in this case, the middle number is going to be what? 7. To the left of 7 is 6. To the right of 7 is 8. Now, when we're doing our number lines, we don't always have to use the number that's directly to the left, directly to the right. It just has to be a number that's to the left and right. So I could choose 0 and 10 if I want to. Just any numbers that are going to fit one to the left and one to the right of our critical value. So at 7, sorry, let's get back to that over here. At 7, what are we going to have? Well, we're not equal to, so we're going to put a circle. And then which way are we going to shade? Are we going to shade towards 6? We're going to shade towards 8. Well, 6 is less than 7, so my shading goes towards the 6 in this case. And so remember, that would include all negative numbers as we go that direction. So negative 5 is less than 7, and negative 20 is less than 7, because the negative is always smaller than a positive number. Okay, let's look at example 1D. Now, same number line, right? Because we're going to draw this, and we're going to have our 7 in the middle, and 6 to the left, and 8 to the right. But what are we going to have at 7? Well, in this case, we're equal to, so we're going to put a dot. And then which way are we going to shade? Are we going to shade towards 6, or are we going to shade towards 8? Well, 6 is less than 7, so I shade towards the 6. And so again, that's what we're looking at those type problems. Now I'm going to add in one more type problem here that I didn't originally have typed in, but I want you to add this to your notes. Call this example 1E, if you will. So for example 1E, let's look at the problem. X is not equal to 2. So what does that mean on the number line? When we draw the number line, 2's in the middle, 1's on the left, 3's on the right. So what is going to happen at 2? Well, we're not equal to 2, right? So being not equal to that value means I need to put a circle. But x could be 1 because 1's not equal to 2, right? If I look at 1 and I look at 3, 1 is not equal to 2, so I could shade towards the 1. But also 3 is not equal to 2, so I could shade towards the 3. So what we see with this graph is that x can be any number along the number line except precisely 2. I can be 1.99. I can be 2.0001, but I cannot be exactly 2. All right, so let's look at some now with solving one step and see what we need to do there. So one thing to remember is that solving one-step inequalities is like solving one-step equations. So if I need to add something to both sides, I still add something to both sides. Or if I need to divide both sides by something, I still divide it by something. But there's one major difference, and I want you to star this, do something, make it really important in your notes. Because there's one major difference between solving inequalities and solving equations. And it's this, that when we multiply or divide both sides of the equation, and you might want to add that in, when we multiply or divide both sides by a negative, we must flip the inequality. Again, when we multiply or divide both sides by a negative, we must flip the inequality. And so we're going to look at a couple examples here of what we're talking about in example 2. So in example 2a, we have that x plus 7 is less than or equal to negative 3. Well, we're solving for x, of course, so it means I need to move this plus 7. And so the 7's there by addition, right? And so I'm going to undo it with subtraction, so minus 7 and minus 7. Remember, what we do to one side, we do to the other. This part cancels, so I'm left with x. Negative 3 and negative 7 gives us negative 10. Now, let's talk about the direction we just talked about. Do I flip this inequality? No, because I did subtraction to both sides. And the operation has to be either multiplying or dividing by a negative. So I leave the inequality symbol as it was, less than or equal to. We draw our number line. Negative 10 is in the middle. To the left of negative 10 is negative 11. Remember, our number line looks reversed on the negative side. The bigger number, right, is further to the left. Negative 1,000 is to the left of negative 100, right? But really, negative 1,000 is less than negative 100. So what are we going to put at negative 10? Well, at negative 10, we've got a dot because it was equal to. And which number fits in? Negative 11 or negative 9? Negative 11 is less than negative 10, so that is the direction that we will shade. In example 2b, we have that 4x is greater than negative 32. And so in this problem, we're going to divide both sides by 4, because remember that 4 is attached to the x by multiplication, and so to undo it, I'm going to do division, right? And so dividing both sides by 4, you get an x. Negative 32 divided by 4 is negative 8. Do we flip the inequality here? The answer is no, because what did I divide both sides by? I divided both sides by positive 4, so we're not going to flip here. It doesn't matter that I divided from a negative. What I'm dividing by to each side was positive. That's what we have to look at. So we're going to draw our number line. Here's negative 8. Negative 9 is to the left. Negative 7 is to the right. At negative 8, we're going to put what? A circle, because it's not equal to. And which number is going to fit? Is negative 9 greater than negative 8? Or is negative 7 greater than negative 8? Negative 7 is larger than negative 8, and so that is where we're going to shade. Let's look at one more example in this group of problems. Here we have x over negative 5 is less than or equal to 7. In this problem, the negative 5 is attached to the x by division. So to undo it, I need to multiply. And so we're going to multiply both sides by the negative 5. So the negative 5 and the negative 5 cancel. I get the x. 7 times negative 5 is negative 35. Do we flip the inequality here? Yes, because what did we do to both sides? We multiplied it by negative 5. And so this inequality is going to flip, so instead of being less than or equal to, it now becomes greater than or equal to, and this is our solution. And so we're going to draw our number line. Here's the negative 35 in the middle. We go negative 40 to the left, negative 30 to the right, and again, you can count by 1s or 2s or 5s or whatever, just as long as you have a number to the left and number to the right. At negative 35, I'm going to have a dot, because we're equal to in this case. And which one's going to work? Is it negative 40 or negative 30? Which one's larger than negative 35? That'd be the negative 30. And so we're going to shade that direction. All right. Last thing we're going to look at is a word problem here. And so we want to talk about how we can take this word problem and write it out and then be able to solve it. So in example 3, you want to buy a new shirt at a department store. You can spend at most $25. Key piece of information there. But not just the 25 is key. What's also key is this word at most. We'll come back to that in a second. You have a coupon for $2 off any item in the store. Write and solve an inequality. Find the original prices, P, of the shirt that you can purchase. And so let's talk about that first key piece of information. When you're dealing with inequalities, you're going to have some statement that deals with what inequality needs to be written, because it's not just equal to anymore, right? So the words at most, when you think about at most, you can have at most 2 slices of pizza at a function before you go back for seconds, right? You can have at most 1 soda a day if your parents so choose, right? So at most means that you cannot be bigger than it. And so the number that is going to be on the left has to be less than or equal to the value that we're told. That's going to be the number on the right. So the 25 is what's on the right. Everything else will be on the left and has to be smaller than or equal to that value. Now, we have a coupon for $2 off, and we want to know the original price of the shirt. So P is the original price of the shirt, and if I'm taking $2 off, that's subtraction, so I'm going to be P minus 2. And so that's our inequality here. Now, to solve this, what do we need to do both sides? Well, we have a minus 2, so that's minus, right? Which means we need to add. So we're going to add 2 to both sides. So P is less than or equal to 27, meaning, and again, remember word problems require word answers. So the price of the shirt can be at most $27. And again, we use that at most from here because we were talking about that before, that it's at most a certain value. Okay, so that's everything for that problem, and that's everything for this lesson. So if you got any questions, make sure you ask. Sorry there. If you got any questions, make sure you ask, and make sure you fill out that Google form. And y'all have a great day.